What specific obstacles in large-scale RL training did the authors identify, and how do these obstacles influence the design of the DAPO algorithm?
The authors identified several specific obstacles in large-scale RL training, including entropy collapse, reward noise, and training instability. Entropy collapse leads to limited exploration, resulting in a deterministic policy that hinders the model's ability to generate diverse outputs. Reward noise, particularly from improperly shaped rewards for truncated samples, can confuse the model about the validity of its reasoning process. To address these issues, the DAPO algorithm incorporates techniques such as clip higher to promote diversity and avoid entropy collapse, dynamic sampling to maintain effective gradients by filtering out low-accuracy samples, and overlong reward shaping to stabilize training by managing the penalties for truncated responses. These design choices aim to enhance the model's reasoning capabilities and improve overall training performance.
Can you explain in detail how the decoupled clip and dynamic sampling policy optimization DAPO algorithm works? Please illustrate the main steps of the algorithm step by step.
The decoupled clip and dynamic sampling policy optimization DAPO algorithm operates through several key steps aimed at enhancing the performance of reinforcement learning in long chain of thought (COT) scenarios. First, DAPO samples a group of outputs for each question paired with its answer, optimizing the policy based on a specific objective that incorporates both the predicted and ground truth answers. Second, it employs the clip higher strategy, which decouples the clipping ranges for higher and lower probabilities, thereby promoting exploration and preventing entropy collapse by allowing low probability tokens to increase their likelihood more freely. Third, DAPO implements dynamic sampling, which filters out prompts with accuracy equal to 1 or 0, ensuring that only samples with effective gradients are included in the training batch, thus maintaining a consistent number of prompts and enhancing training efficiency. Fourth, it introduces a token-level policy gradient loss, which assigns greater influence to longer sequences in the overall gradient update, allowing the model to learn from high-quality long samples more effectively. Lastly, DAPO incorporates overlong reward shaping, which applies a length-aware penalty mechanism to manage the rewards for truncated samples, stabilizing training and reducing noise in the reward signal. These steps collectively contribute to DAPO's ability to achieve superior performance in tasks like AMY, as evidenced by the significant accuracy improvements observed.
Could you provide a specific example that illustrates how the dynamic sampling technique addresses the gradient decreasing problem in GRPO?
The dynamic sampling technique addresses the gradient decreasing problem in GRPO by filtering out prompts that yield an accuracy of 1 or 0, which would otherwise result in 0 advantages and no gradients for policy updates. For instance, if all outputs for a particular prompt are correct and receive the same reward of 1, the advantage for that group becomes 0, leading to a lack of gradient signals for training. By oversampling and ensuring that only prompts with effective gradients are included in the batch, dynamic sampling maintains a consistent number of prompts that contribute to the training process. This strategy not only prevents the effective number of prompts from decreasing, but also stabilizes the gradient signals, thereby enhancing training efficiency. Empirical results indicate that this approach allows the model to achieve the same performance faster, demonstrating its effectiveness in mitigating the gradient decreasing issue.
What empirical or theoretical improvements does the proposed method offer over traditional methods like GRPO and PPO, particularly in the context of long COT reasoning tasks?
The proposed decoupled clip and dynamic sampling policy optimization DAPO algorithm offers several empirical and theoretical improvements over traditional methods like GRPO and PPO, particularly for long chain of thought COT reasoning tasks. Firstly, DAPO introduces the clip higher strategy, which mitigates entropy collapse by promoting diversity in sampled outputs, thus enhancing exploration capabilities and preventing early convergence to deterministic policies. Secondly, the dynamic sampling technique addresses the gradient decreasing problem by filtering out prompts with uniform accuracy, ensuring that only samples with effective gradients contribute to training, which stabilizes and accelerates the learning process. Additionally, the token-level policy gradient loss allows longer sequences to have a more significant impact on gradient updates, effectively penalizing undesirable patterns in lengthy responses, which is crucial for maintaining quality in long-caught scenarios. Lastly, the overlong reward shaping mechanism reduces reward noise associated with truncated samples, stabilizing training and improving overall performance. Collectively, these innovations lead to a notable performance increase, achieving 50 points on AIME 2024 with only 50% of the training steps compared to previous state-of-the-art results.
What methodology was used to validate the performance of the DAPO algorithm, including specific benchmarks or metrics? How did the results compare to existing approaches?
The performance of the DAPO algorithm was validated using the AIME 2024 benchmark, where it achieved a score of 50 points, surpassing the previous state-of-the-art result of 47 points achieved by DeepSeek R10 Quen 32B, despite using only 50% of the training steps. The evaluation involved repeating the evaluation set 32 times to ensure stability in the reported average accuracy. Key metrics monitored during the training included the length of generated responses, dynamics of reward, and entropy of the actor model, which were crucial for assessing training stability and performance. The results indicated a significant improvement in accuracy, increasing from a mere 30% with the naive GRPO baseline to 50% with DAPO, demonstrating the effectiveness of the proposed techniques in enhancing RL training outcomes. Overall, the DAPO algorithm not only outperformed existing approaches, but also provided insights into the model's reasoning capabilities through its dynamic evolution during training.
What are the key limitations of the DAPO method as identified by the authors, and how might these limitations impact its practical application in RL training scenarios?
The authors identify several key limitations of the DAPO method, primarily related to the challenges of entropy collapse, reward noise, and training instability. Specifically, the initial naive GRPO baseline suffered from entropy collapse, leading to a lack of diversity in generated responses, which can hinder the model's exploration capabilities. Additionally, the reward shaping for truncated samples introduced noise that could confuse the model regarding the validity of its reasoning process, potentially impacting the quality of the generated outputs. The authors also note that the sample-level loss calculation in GRPO may disproportionately penalize longer responses, which can lead to unhealthy increases in entropy and response length. These limitations could significantly affect the practical application of DAPO in RL training scenarios by reducing the model's ability to generalize and effectively learn complex reasoning patterns.